Good morning, Year 13. What I've done is cobbled together some notes to explain some of the work that I've set for today. The thing that we are looking at today is the ionic product of water, which is called the KW. Now, before I go on to that, I need to actually explain two concepts that we talked about last lesson, but we need to develop more of this lesson in order to develop the basis for understanding. Now, last lesson we defined the Bronsted-Lowry acid as a species that is able to donate a proton. We then also looked at the Bronsted-Lowry base, which is a species that is able to accept a proton. Now, I talked a little bit about the fact that H plus is how we represent a proton. However, that isn't actually scientifically the case. It has to be another species because a single proton on its own can't exist. But that will be explained a little bit more in the notes today. So, based on those definitions, water itself is a bit of a weird one, because if you put an acid in it, so for example hydrogen chloride, okay, which I've got on the book, you can see here, if I put hydrogen chloride into water, the hydrogen chloride dissociates in the water to form what is essentially H plus ions and Cl minus ions. Now, this was the species that I identified last lesson as being the actual species, which is a proton. So this is what a proton would actually be. So I could write it down like that, or I could actually put H plus. But what that doesn't do is show the role that the water actually takes as being a base in that reaction. From this you can very, very clearly see that it has accepted a proton because it's gone from H2 to H3, and the chlorine has lost that proton. So that's why this is important as a way of simplifying it but not showing the role of water. This now shows the role of water acting as a base. Here what we've got is the H3 plus ion. It's actually called the oxonium ion. Please make sure that you remember that it's called the oxonium ion. However, you will also see it referred to as a hydronium ion or the hydroxonium ion. So it's three names for the same thing. And I do apologise for the fact that it is three names for the same thing. So it's the oxonium ion is how we will refer to it in the textbooks and on the exams, but it will also be in common parlance be referred to as the hydronium ion or the hydroxonium ion. Please keep an eye out for that. Now, the second example was where it acts as a base, as an acid, this time donating a hydrogen to another species. Now, what you can see here is that we are reacting it with ammonia. So the hydrogen, the water here, reacts with the hydrogen, ammonia. It donates a hydrogen to the ammonia to make an ammonium ion, and it becomes a hydroxide ion. Okay, so there's a H there, an OH minus there, so that's H plus. So you can see that in nearly all cases, what we are getting is it either dissociating to become a H plus ion, or in this case, it's actually dissociating to become an OH minus ion. So what that actually then links into is something called the ionization of water. Now, water itself is a polar substance, as we know, polar substance because, it's a polar substance because it has the oxygen ion, it has the oxygen atom, which is much more electronegative than the hydrogen. So what you end up with is an induced a dipole within the molecule. That's why it's got hydrogen bonds. But what can also happen is it can become ionized, and that word "slightly" is actually very, very important, and I will come back to that later on. what we've got here is a hydrogen water, so it is a water molecule in its liquid phase. Okay, so this is H2O liquid. This will dissolve or ionize to become the hydrogen ion in its aqueous form. So remember, that's a dissolved ion within a solvent, and a hydroxide ion, which is also dissolved ion in a solvent. So that's why this is aqueous. So you must remember the changes of state in this. So we've done this idea, and I've simplified it again. I do apologise for that. The reason why I've simplified it is that when we were talking about chemical reactions, we were actually talking about the H plus ions and the OH minus ions. But what actually happens, and this is not a mistake with me writing this out in this way, what I've got is I've got here a water molecule in its liquid phase, and this is also a water molecule in a liquid phase. However, what is actually happening is this water molecule is accepting a proton to become the H3O plus ion. So this molecule, because it's accepting a proton, means that it's acting as a base. This one is donating a hydrogen molecule, a proton, and is dissociated into the OH minus. So this one is acting as an acid. So that's why I've not done it as 2H2O, because I wanted you to see that one molecule of water is acting as an acid, the other molecule of water is acting as a base. And because of that, what we then get is this H3O, so H3O plus ion and the OH minus ion. We often abbreviate this back to H2O dissociating or ionizing into H plus and OH minus ions. So whenever we see H plus ions, actually what we're referring to is the hydroxonium ion, or the oxonium ion, which is this one. Okay, I'm hoping that you're following that. Now, based on that idea, I hope you do like my do table, because it's got doogs, as my daughter calls it, or doogies, or whatever I actually calls it. She changes the name randomly. Okay, so if we apply what we know that H2O liquid dissociates into H plus and OH minus ions. From that, because we've got this equation, we've seen this before, where we've taken substance A and substance B reacting reversibly to make substance C and substance D. When we've done that before, we've introduced used the equation Kc, which is the equilibrium constant. And this equilibrium constant is a way of working out how much of it is in the products form and how much of it's in the reactants form. So when we've worked out Kc, we've got products over reactants. I'm not going to go into the full details on that because it's a little bit more complicated than that. You will need to go back. So remember, if we've got, say, 2H2O, then that would actually be the product, and we put square brackets, which means concentration, and we put a squared after it because there's two of them. So you need to go back to that if you need a refresher on it. But for this case, because it's 1 to 1 to 1, we don't need to put the powers after it. So it's Kc is equal to the products, which is H plus ions and OH minus ions, over water. Now, we've got to make a few assumptions here. Please bear with me. These assumptions won't make sense, but they are logical. Okay, so if we make the assumption that it only slightly ionizes, what we actually mean by that is, if we look at the water molecule, about 1 in a million or 1 in 10 million of them will actually undergo this dissociation. So we end up with 99.9999999 and keep going until we get 7 digits here after the decimal point, and we'll then get approximately 0.00001% of it is in the hydrogen H plus form, and exactly the same, because this splits up into one of these and one of these, exactly the same number of hydroxide ions. That is important. Okay, this is such a puny, pathetic percentage that it's almost unbelievably, and you wouldn't even bother thinking about it. So we actually then make a second assumption. We say that if we round this up to any normal number of decimal places, which we can be accurate about in science, which is generally a maximum of 2 or 3 at A level, that if we round it up, this will immediately return back to 100% when you round it. There is a tiny bit that you have to go 7 decimal places back before you can find it. So what we say is that allows us to simplify this reaction a little. We know that there's still this tiny amount of hydrogen ions and tiny amount of hydroxide ions, but because this has been rounded back up, we can assume that this is 100%. So what we end up with is that the Kc, the equilibrium constant, is equal to the hydrogen ion concentration times the hydroxide ion concentration over 1. Now if you divide anything by 1, the answer is going to be 1. It's going to be the same number, isn't it? So this is not going to affect it. So what this gives us is something called a modified equilibrium constant. And essentially, because it's a modified one, we change the name of it slightly. So what we get now is something called Kw, which is actually the ionic product of water. What it's saying is, if I've got water, it will split up to form, and it won't be a reactant because it'll just split up into these two, into form H plus ions and OH minus ions. Okay, so that's the ionic product of it. Now, what that does, though, is it allows us to come up with a few assumptions. So, for example, if we actually mathematically work out what Kw is, okay, going back to our definition of equilibrium constant, basically we have to form them from their ions and their standard states, we have to undergo the reaction, it has to be under standard temperature and conditions, so 298K, or 25 degrees Celsius, so you've got 298K. When you undergo that reaction and do the workings out and do the mathematics for it, you find out that Kw is actually a constant. And that constant is 1 times 10 to the minus 14. Sorry, I do apologise. 1 times 10 to the minus 14. Now I'm going to pause there for the simple reason I want you to think about the units. Please pause the video, give yourself 2 minutes to have a go at the units or working out what the units are. Okay, welcome back. Well, and pause there for the units. Basically what I want you to do, because you were thinking about this, you've got H plus aqueous over OH minus aqueous, times OH minus aqueous. Now remember, square brackets means concentration. Concentration itself is measured in moles per decimeter, so that's moles, decimeter to the minus 3, times moles, decimeter to the minus 3. So that's going to equal moles times moles is moles squared. decimeters cubed to the minus 3 times decimeters cubed to the minus 3 is, remember when you multiply indices, you actually add them. That, and adding two negative numbers makes it more negative, so it's decimeters to the minus 6. If you remember, KC had different values for every single time. KW is the same. So when we're looking at KW will actually have the units moles squared decimeter to the minus 6. So that's moles squared decimeter to the minus 6. Now, what that allows us to understand is this. Okay, so that'll be moles squared decimeter to the minus 6, 1 times 10 to the minus 4. Now, if we know that that's a constant, what we can do is go back into this equation and do this. 1 times 10 to the minus 14. I'm not going to put the units in this one. Is equal to the concentration of hydrogen ions in their aqueous form multiplied by the concentration of the hydroxide ion in their aqueous form. However, if we logically think about this and go back to the equation, H2O dissociates, and I'm dropping the state symbols now just because, actually no, better not. H plus aqueous, OH minus aqueous. We find that they're in the ratio of 1 to 1 to 1. So what we can actually work out from this is if these are in a ratio of 1 to 1, we can actually say that the hydroxide ion actually is the same as the hydrogen ion. Now what that allows us to do is, instead of saying H plus times OH minus, well, if the two values are the same, isn't that H plus squared? So we can actually say 1 times 10 to the minus 14 is equal to the concentration of the H plus ions squared. Now, if you're starting to think ahead on this, what you actually work out is this. Then that's now only one constant, one unknown. So what we can actually do from that is, at equilibria, we can work out the concentration of hydrogen ions at 298K. And that would be equal to the square root, because it's squared there, so we square root the other, square root both sides to remove it. So the concentration of H plus ions is equal to 1 times 10 to the minus 14. So in this case, concentration of H plus ions is equal to the square root of this. I'm going to put 2 there. Now if you're square rooting a number, it's the same as dividing that power by 2. So what you end up with is 1 times 10 to the minus 7 moles per decimeter. So we now know the concentration of H plus ions. Think ahead, think ahead. What do we know from last lesson? Well, pH is equal to negative log of the H plus ions. So if I put this value into the pH equation, I end up with it being, oops, that's not a minus sign, minus log of 1 times 10 to the minus 7, close brackets. If I stick that in a calculator, I end up with it being pH 7. This is why pH 7 equals neutral. Now, I hate that comment. I hate that comment with a vengeance. The reason why I hate that comment with a vengeance is that is putting an arbitrary value and saying, oh, if you're at pH 7, that means it's neutral. What does neutral mean? Actually, neutral is the point, if I go back to this equation, keep harping on to this equation, with a concentration hydrogen. So neutral is actually equal to the point where concentration A plus aqueous ions is equal to the concentration of OH minus aqueous ions. That is what neutral actually means, that there is an equal balance of H plus ions and OH minus ions. Okay, that is massively important. That value 7 is great, but there are issues with this. What we need to do is step past that as A-level students and go, actually now, we know that a solution is neutral when it has an equal concentration of H plus and OH minus ions. The reason for that is this value, 1 times 10 to the minus 14 moles per decimeter cubed, 1 times 10 to the 14 moles squared decimeter to the minus 6, is based on the dissociation at 298 K. Now, when we looked at this topic in the end of year 12, we said that the only thing that can change Kc, which is the equilibrium constant, was the temperature. Okay, and we had that with the bell curve. We said that if that is the activation energy, if we change the temperature of a curve, if we change the temperature of the solution, what happens is the total area underneath that curve must remain the same. So that's the total area, because it represents an overall image of the energy of the particles. So what happens if we increase the temperature was that this curve would be shifted. It becomes less in height because it has to be, because you can't have it the same height, otherwise you'd have to have because the area under the peak has to be the same. But what happens then is we end up with a greater proportion of the particles that have energy greater than activation energy, so that will actually affect the position of equilibria. Because we've got more particles that have energy greater than the activation energy, we are going to have more particles that are more likely to collide, so the equilibria is going to be shifted to affect that. And that is the same with Kw, because it's a modified equilibrium constant. Remember, it's a modified equilibrium constant. This is is actually affected by temperature. Okay, so what does that mean? Well, as confusing as this seems, the position of the equilibria can change, and it is changed by temperature. But what that actually means is this. If I've got H2O liquid being dissociated into H plus aqueous plus OH minus aqueous, when we spoke about this earlier, we said that this was 99.91234567%, and this was 0.00001%, and that would be the same, ... okay? What happens if I increase the temperature? Well, if I increase the temperature, I will get more particles that have sufficient energy to overcome the activation energy, so a greater proportion. However, all that means is if I increase the temperature, what will actually happen is this might change from 999 to that. So obviously this would change to that. If I've got the decimal places right, bear with me on that if I haven't. But this will still be equal in number. Now, if I stick that into my decimal point, or work that out on the decimal point, what you will actually find is, say, if I go from 25 degrees Celsius and then change it to 40 degrees Celsius, at this point, KW would be equal to 1 times 10 to the minus 14.
The answer is minus 25.
Thank you, Phil. I really appreciate you working that out for me. Don't know why. Okay, whereas at 40 degrees, this might have actually changed, or this will change to 10 to the minus 14. If I do the same mathematics with this, what I will find out is that actually by raising the temperature by 15 degrees, the pH of the solution will raise to 6.8 degrees, at 6.84 degrees, and still be neutral. Okay, so pH 7 is not neutral. Neutral is when you have an equal number of positive ions, so hydroxide ions and hydroxyl ions. So hydroxide ions and hydrogen ions. Good grief. Okay, that is when pH is neutral. That at higher temperature occurs at 6.84. If I increase the temperature to 200 degrees, it can drop down further. If I make it colder, the pH will increase. So it will be pH 7.6 before it's neutral. So please move away from saying that pH 7 is neutral and understand that pH is neutral when you have the same number of hydrogen ions and hydroxide ions dissolved in your solution. I'm going to stop the video there. That will explain section 3 in a bit more detail. Section 4, you should be able to read for yourself and be able to work that out. It's nice and simple. I needed to explain this bit, okay?